Okay. So welcome Professor Yuke Zhu to visit us. How many of you are planning to submit for Coral 2026? Conference on Robot Learning 2026? Okay, just let you know because the program chair. So general chair. Yeah. Okay.
Welcome to Austin. Yeah.
Yeah. So the next year, Coral will be in Austin, and Yuke will be the general chair. So Yuke is a associate professor in the computer science department at UT Austin, where he directs the robot perception and learning (RPL) lab. He's also a director and distinguished research scientist at NVIDIA, where he co-leads the GEAR lab, Generalist Embodied Agent Research Lab. He focuses on developing intelligent algorithms for generalist robots and embodied agents to reason about and interact with the real world. He obtained a PhD degree from Stanford, and he received a lot of awards. For example, NSF Career Awards, the IEEE RAI's Early Academic Career Award, and many other faculty fellowships, such as like research award from Amazon, JP Morgan, and Sony. On the personal side, when I interned at NVIDIA in 2020 summer, like 5 years ago, Yuke was my mentor. Now I have two PhD students who interned in GEAR, and Yuke is still their mentor. So I guess it closed the loop. Yeah, without further ado, let's welcome Yuke one more time. Yeah.
All right. Can you hear me right? Happy Halloween, everybody. I was kind of expecting somebody walking with a robot costume, but I see there's a parallel geographer. Today, as the title suggests, I'm going to talk about humanoids. Maybe before I talk, and I just want to get a sense, like, so what's the perception of the audience on humanoids? How many of you believe that we're going to have humanoids in homes doing all the kind of like everyday chores for us in the next 5 years? Raise a hand. 5 years. 10 years. Well, that's a lot. That's like I think half. What about 50 years? Okay, almost like I think I saw people are good. Like so, it's optimistic. So as the title suggested, I'm going to talk about some of my recent work on humanoids, but also I want to spend some time discussing like so what are the opportunities and also challenges, right? So there's definitely a lot of exciting developments in this field, but also a lot of work to do. So I think like many of you have seen this picture. This is a thing of GTC 2024, and it's an NVIDIA conference in San Jose, California. This happens last March. A bunch of humanoids are standing on the stage of GTC keynotes, and there's only one biological one, that is Jensen Huang, the CEO of NVIDIA. During this keynote, and he announced that we're having this new team called GEAR, Generalist Embodied Agent Research. This is gonna co-led by me and my long-term friend and a collaborator, Jim Fan. So with the goal of building full-stack AI solutions for humanoid robots. So you might wonder why humanoids and why suddenly this become a thing, right? So and all the videos of humanoid robots are flooding the social media. When I was always browsing Twitter, I see this all the time. And for those of us like who had hands-on experience with physical robots, we know the amount of pain and suffering to get even a simple robot arm to work properly, right? So and the humanoids way harder given the amount of sensors and technical components, like a higher degree of freedom, right? So it just kind of compounds the challenge with all the whole body control, with the dexterous hand, with the kind of safety requirements. A lot of things can go wrong. And also like take a step further, like so why humanoids now, right? Like all of a sudden, like so both the industry and academia become so captivated by human-like robots in recent years. So what happens and to make the change? So one thing I would say that humanoids is by no means a new concept, right? So the dream of building human-like machines and has fascinated people for centuries. And if you search for Da Vinci robot, Leonardo's robots, and you're gonna find a humanoids back then, right? So when like Da Vinci built himself. So definitely people have been enchanted by the idea of creating human-like robots and machines for like many years. But it's only until about like 50 years ago that the technologies get to the stage it's kind of good enough for researchers and engineers to actually give a try to be serious about building such a such human-like robots. So in the past, so there's like several waves and the up and downs of humanoid robotics, but they haven't really kind of reached a big commercial and business impact yet, right? So and then what happens about 10 years ago, the DARPA Robotic Challenge was kind of a harsh reality check. That kind of really shows like how difficult it is to put humanoids in actual practical useful tasks, and even with human teleoperation, with human supervision, is hard. Maybe like so online that you can find videos of like this kind of epic falls of humanoids. It kind of reminds us like all the challenges that we do. And so this is a challenge actually CMU did quite well. I think there's #2 teams like so globally, but still like so there's a lot of like critical cases like so encountered there. But kind of leads to the whole thing leads to a humanoid winter. Like so for a couple of years like so the resources and investment died down. Only until recently the AI and the hardware development has given kind of people a new hope in creating this human-like robots. New humanoids are now popping up like a mushroom, right? So like so from time to time, every month I see a new robot like so released by some companies or startups. So I call this kind of the Cambrian explosion of humanoids. Suddenly we have so many like humanoid fishes. Like so, what's going on here? Maybe this time is different. So I understand that this can still be a somewhat controversial opinion whether we should be working on humanoids or maybe like the center robots first. But personally, I'm quite bullish on working on humanoid. I think there's a couple arguments from a robot researcher's perspective why humanoid. So there's of course a lot of roles to play with more specialized robotic hardware and robot arms, quadrupeds. But if you're passionate about building general purpose robot autonomy, I think like so because they are physical agent, the hardware embodiment is important because their hardware embodiment determines their capability envelope, right? So if you work on quadrupeds, you at best get a dog level intelligence, right? So if we're talking about physical AGIs and so general purpose autonomy can be deployed in household tasks, you do need something that have the versatility to perform everyday tasks like a human. The second is like, I think the costs have dropped dramatically over the past 2 decades, and going from this custom build one of the kind hardware that costs $1 million, like the NASA Robonaut, to some commercial hardware now you can buy online and ship to your home, right? So this new hardware are not only cheap but also quite robust and capable. So here, this is a recent work. So we have collaboration with Guanya's lab led by his student as an intern at Gear that we showed us we can use reinforcement learning and sim-to-real transfer to recreate this agile athletic movement on this kind of Unitree G1 robot at the price of a car that you can buy. And the third is we call humanoids a brownfield project, not a greenfield. That means that like, so we human build a world for our human form factor. So if the robot shares a similar physics, in principle, they can easily integrate with our existing infrastructure. That means we don't need to turn down all the like apartments and factories, build new ones for the robots. So we can just roll in the robot to the existing environment and use all the tools and equipment we designed for humans. So a lot of questions when I got like so what is a humanoid? Why we need to have legs and whether they need to stick to the human form factors closely. So I visited Japan last December, and this picture is taken from a lab called the Future Care Lab, where they build a future technology for senior care in Japan. That they show me this model home. That's a very classical, traditional Japanese home with all the stairs and narrow corridors. So when I asked the researcher there why robots need legs, and this is the example they show me, right? So if you are to build robotic technology that can benefit the humanity, you want to make sure this is available and accessible to all the individuals, including the grandmas that are living in old Japanese homes. So, and then as a researcher, I think we all care about real-world impact. During the launch, I think there are some discussions how do we create the impact both research-wise in academia and also product-wise in industry, right? So I think as we have been seeing that like the advanced economy are getting older and the labor shortage is now becoming a global issue, and robotics is really shifting from some kind of futuristic novelty to the essential technology to solve some of the most pressing problem like so society collectively face with, right? So for those of you who are also have a passion and ambition to create a robotics business, I think there's a big economic opportunity come with us as well. So it is estimated that a $50 trillion of annual global GDP goes to tasks that involve physical labor. So what that means is that you don't need to build a solution that solves all cases, right? So if you can automate 1 or 2% of the physical labor tasks with some robotic solution, that's a $1 trillion business. And the last, I think, is as a technologist, as a robotic researcher, what I care about is the data access, right? So there's no internet of robot control, unlike LLM and VLM, who have the luxury to download a huge amount of text and videos and images online. We cannot download robot control from the internet, but there's a ton of human-centered data, like so sitting around, like from the motion capture database, from the Hollywood and the entertainment industry to all the YouTube and TikTok videos of showing human doing all kinds of everyday activity, right? So having a closer form factor potentially allows us to tap into this kind of human-centered data source. So this is a hypothesis, right? So whether humanoids make us like be able to leverage this human-centered data. So to validate this data hypothesis, we recently investigated whether humanoids make it amenable to learn from human video. So this is one of the recent work that we did last year called autonomy, that we introduced a method that takes only a single human video demonstration as input and is able to recreate the same motions and same behavior with the humanoid robots in various settings with different objects. So the idea is a two-stage approach. We first build a pipeline to understand human video. You can imagine that we are using some vision foundation model to track the human hand, reconstruct the object in the videos. So that forms some kind of a reference manipulation plan. It captures which the objects are moved in the video, and also how the human body move between the adjacent subgoals, in the manipulation plan. And then the humanoid motion can be sensitized through some object over targeting. We essentially morph the humanoid motion to the object location at test time to realize the subgoals in the manipulation plan. So this method kind of works well on a variety of objects, and we apply to from a single arm to bimanual manipulation. Some are pick and place, some requires a bit more dexterity with a multi-finger hand, or even manipulating with articulated objects. So that's kind of an initial showcase of how we leverage learning tools to learn from human video as a viable data source for humanoid training. So as maybe most of you should know that there's an ongoing trend in robot learning is moving towards scaling and a large model training, so-called foundation model. So there's a data-centric trend going on following the success of foundation model in other domains of AI, such as natural language processing and computer vision, right? So usually, this kind of like a foundation model training follows this same recipe that you scale up large-scale data sources that might come from different heterogeneous source, and then you train a general large-scale model, typically using transformer as a backbone, and then once you build a base model, you can specialize this base model for downstream application, just like how large language models are used. So to investigate this kind of data-centric paradigm, we introduced the Groot N1. So this is like the first open source model released from the Gear team at NVIDIA. That it allows this two dual system design that inspired that this kind of vertex thinking slow and fast, right? So you can think about there's a big brain serve as a system to does all the reasoning and planning. So it maps the image observation, language instruction to some latent token that get passed to the system one, which is model as some kind of diffusion transformer for action generation at high frequency. So the entire model can be trained end-to-end with some demonstration data, right? So that come with the observation, language, and action pairs. So the model is open source, available if you search for Isaac Groot, and you are gonna find this model, and people have been using this model, fine-tune and deploy on all kinds of different problem domains. So the Preacher model already have a quite strong generalization capability. It can follow language commands and to perform tasks across different objects, across different task goals. But for the tasks that's a bit harder or more challenging, you can post-train the model to do a bit more interesting things, right? So like this one that you can be a bit romantic, right? So you can pick a flower and hand over a champagne. A disclaimer that I don't support robot-human dating, right? So human should date human, robot should date robots. And models can also be post-trained side by side. There's the two robots running two good policies post-trained on this industry task and to perform this kind of like a handover type of task in assembly line. So these are the kind of like a capability of such model. And when it comes to foundation model building, I think a lot of the question goes into what's the model architecture, right? So how do we better scale? How do we handle the challenge of generating action as a high frequency so that we can run that in a real-time system? But I think an equally important question, or maybe more important question, is how do we train the model? Because like we don't have such a data source like the luxury of LLMs. So about 2 years ago, I kind of introduced this concept of a data pyramid. So back then, I was a assistant professor, so I was kind of trying to do this research in foundation model, but there's simply no data set. I was kind of just scrambling to find whatever data sets are available. So back then, it was a very pragmatic approach. I was just looking around, see what data are useful for training my robots. And I kind of like identified these 3 data sources that I organized that into this pyramid structure, right? So at the bottom level is the web data. So like the YouTube videos and Wikipedia pages, and all the kind of images and showing human doing kind of like interesting daily activities. So these are kind of like a unstructured multimodal, and it's kind of passive observation of the physical world. But there's tons of them. Actually, like the human world collectively generates exabytes data per day on the internet. Exabytes is a huge number. It's a millions of terabytes, right? So there's tons of like a data we can leverage. And the middle layer is a synthetic data. These are the things that come from physics engine, graphics renderers, now like potentially even neural models, right? So you might see like, so we can get infinite amount of synthetic data if we can just run the simulations forever, given enough compute. But in reality, it's hard to scale such synthetic data sources because the quality matters a lot. Otherwise, you got a similar real gap. And the top level is the real robot data. Real robot data are definitely important because they are arguably the highest quality data. They come from real sensor, real hardware, real motors. So there's no reality gap. If you train on real data, you can directly deploy the model to the real hardware. But the challenge is like, so you can only collect a 24-hour data per day on one robot. Even that is overestimate because the collecting data turns out to be super hard, right? So with a real robot, this is a time lapse of our real robot data collection effort and video. You see that we run a massive operations, and for operating one robot for data collection, you at least 2 or 3 contractors. Like somebody needs to come to reset the environments, and sometimes they're doing the computer running some scripts or doing some labeling, and then like there's a teleoperator that then stand there, so use the glob like to remap the actions and to the robot, right? So it's a massive operation. Well, in Silicon Valley, I would say like, so there are still a lot of companies are looking at this paradigm as a way to scale data sets, right? So, but it remains an open question, I would say, like, so whether we can solely rely on real world data to get to the level of generalization we need to build like so really generalist robots. So for me, it's a bit unclear to me. And what's the bottleneck is fundamentally there's a limit to scale because it only scales linearly with respect to the money and time you put in. So personally, I kind of bet on synthetic data as a way to supplement the lack of real data, right? So the nice thing about synthetic data is like when simulations build, we can very deep access to generate exponentially many data points, like showing here, random texture, lighting, objects. So we go from linear to exponential. When it comes to data size, we like exponentials. So however, synthetic data has historically been difficult to scale because it requires a graphics designer like a manually curate authoring those assets, and then you have to tune the physics and with somebody who really understands the physics engine, and then you put them in and make sure like so all the objects are in the right place to follow some kind of statistical prior of how the real world looks like. It's just a tedious progress, right? So process. So what really changed the equation, why it make synthetic data to make sense, is the availability of generative AI tools. Now we have much better models that are trained on huge amount of internet data sources that capture those kind of ecological statistics of the real world. So our first attempt to use this kind of generative AI models to create simulation environments called Libero. So it built a pipeline to turn language description of a class into some formal language. We use PDDL as a base to specify the simulation environment, and then that kind of PDDL format can be turn into a physics engine to spawn up like so simulation runtime. We use this kind of procedure generation tools to create a set of simulation benchmarks for evaluating lifelong learning agents. So you can kind of go, you can test out the spatial generalization versus the goal generalization versus the object generalization in different axes. But turns out, like, so when we kind of like release Libero, and it was a quite challenging benchmark to us. Like, so our goal is to see how lifelong agents perform in this. But maybe it's kind of easy to use. We did a good job with all the data sets and the open sourcing that it got picked up by the booming community of VOA models, right? So and people are not using this for lifelong learning. They actually treat this as a multitask benchmark. They fine tune post-train their VOAs on this benchmark and report numbers on this. So this is kind of becoming a very popular practice. So it's kind of amazing, right? So after we released last year, how fast the progress goes, right? So when we released, I think the baseline number was a 40-50% success rate. And now that you see that quickly it gets up to like 80s and 90s. And actually today we released a paper for PLD that's led by an intern at Gear who was going up student called Wendy. So which shows that we are able to get a 99.2% success on Libera. That's kind of game over, right? So yeah, and this benchmark is solved and with some kind of online RL fine tuning to close the last mile of the gap, performance gap. So this is a kind of like becoming too easy for this frontier models, and so that kind of like motivates us to seek a bigger challenge. So after Libera, we start thinking about building Rubacasa, where we use Gen AI tools and to create this realistic simulation of a human-centered environment. Now we are moving from a tabletop to a building-wise things. We use a Pepsi 3D model to generate all the assets, and LLMs to generate all the paths and write reward functions, and then we run image generation model to randomize all the textures and the background, right? So that allows us to create a large set of kind of a human-centered ecological environment that kind of without any kind of hard coding, right? So everything is automatically by coding a bunch of AI models. Now that we have a Rubacasa, this is already open source released. And we also want to create a benchmark on top of that, right? So to allows us to systematically bench the next generation of VLA models or the Ruba Foundation models. So soon we're going to release a new benchmark that built on top of Rubacasa called Rubacasa 365. So as the name suggested, 365 tasks, and so that are spanning around 2,500 different kitchens, and they are all carefully designed kitchens with like 2,000 hours of human demonstration. So they are not machine generated, complete human tally of data. This will be fully open source for the community to use. And we also benchmark the state-of-the-art vision language action models, including Pi and also Groot. And I think even the best model kind of struggle to perform well in this task that requires like multi-hop long horizon reasoning, right? So they can achieve like, so the best model is like 20% success rates. So there's a long way to go. Okay, so now we have the simulation environments, actually a lot of them. Like so, but to be able to use them to train the foundation model, we also need the action data, right? Where is the action from? So we kind of developed this Sixter project called a Dex Mimic Gen. It is a system for automatic robot trajectory generation. So intuitively, you can think about that as a trajectory multiplier that you just let a human tally out like 5 to 10 times, just get a handful of human demonstration data set in simulation, and then you can let compute do the job, right? So you can leverage simulation to spawn a large volume of demonstration. So how does it work? So let me use this example to illustrate. So just say that, so now the current subtask is to pick up a mug with a robotic ripper. Then you can randomize the object in a new location, and then you want to synthesize the trajectory to the new object, the mud placement. So the way we do that is by transform the trajectories from the source demonstration to the target demonstration based on the new mug location. And if you look closely, right, between these two, there is something that stays invariant, which is the relative pose between the robotic hand, also the mug, right? So that in some sense you can imagine we're doing this data generation as achieving some form of functional equivariance that preserve the SC3 transformation between the robotic end factor and also the object. So this was similar to what we have done in the Okami project I showed you earlier, that how we do the object-aware retargeting with respect to the object location. So using this, we can generate a lot of new demonstrations with new object initialization. But to extend the system to humanoid robot with dexterous hand, there's additional housekeeping we need to do, because now we have 2 arms, we have dexterous hands. So we kind of identify 3 modes of coordination behavior between the 2 arms, right? So in total, you can have 2 arms that they are doing 2 different things and completely independent from each other. You can have coordination behavior, like the 2 arms needs to coordinate together to pick up like a heavy object. Or you can do sequential things. You have to pour one thing and then like the second arm can do the next subtask, right? So to be able to handle this different coordination behavior, we kind of needs to build a state machine logic that allow the system to transit from one mode to another. So how this data generation system works, like, so we just keep running the dex imaging system to generate more and more data from 50 source demonstration to 3,000 trajectories, and like let it run, like see how that goes. And then we train a policy on a larger and larger data set. We see that so there's a steady increase in performance as we train on the larger data sets. So the question is, what if we keep running the compute and we got 3 million trajectories? What would happen? Boy gets 100. No. Yeah. So because the particular way we generate data lacks diversity, because for some corner cases it won't be able to successfully synthesize the demonstration for that particular object placement. So as the demonstrating data sets reach a certain level of diversity, it just plateaus, right? So and then it just keep regurgitating same trajectories again and again. So there's still open research to be done to increase the diversity coming out of this system. Okay, so now we combine RobotCasa's ability to procedurally generate large simulation environments with DexMimagen's ability to multiply trajectory from human demonstration. We can create a large set of synthetic robotic data sets that significantly supplement the small amount of real robot data. All right, so the top part of the pyramid. So we kind of develop an effective strategy to use semi-real data together across the pyramid, the 2 top level of a pyramid, to train the robot policy. And concretely, the way that we create simulation environment is called digital cousins. And the word digital cousin was coined by this Stanford paper that I cited at the corner. You see cousins, meaning that probably you heard the word digital twin, right? So twin is a 1-to-1 digital copy of a real environment. But you know that so cousin means that you look like your cousin, but not exactly the same, right? So we're kind of giving up some precision, but we get a lot more diversity. And as this video shows, actually the first and the third columns are how the real world scene looks like. These are the kind of target test environment that we evaluate our humanoid robots on. And the second and fourth are the digital cousins we create, right? So if you don't look close, so you see there's a lot of ballpark similarities between sim and real, right? So, but if you look really closely, well, they don't look exactly the same, right? So there's still a lot of discrepancy between the 2. So the question is, how do we leverage the abundance of simulation data in this setting with digital cousins? So the kind of particular strategy we introduced is called co-training, which is a quite simple yet quite effective strategy to leverage this the asymmetric data sources. So the co-training pipeline goes like this. So in the first place, we have a task set up. Say we have a task in mind that we want to solve in the real world with a robot. And there's also a lot of prior simulation data we just download from the internet. So these are the prior data that coming from previous projects or open source release. All right, so these are the things that we have at the beginning of the co-training. And so we first run the tally operation to get some source demonstration on the real world. We create a digital cousins in simulation using procedure generation, and then we can use the DexMimagen pipeline to generate tons of trajectories with the digital cousins. And then now we have these 3 data sources, right? So real world demonstrations, small scale, digital cousin demonstrations, prior simulations. And the way that we leverage them is by just sampling mini batch from all 3 sources and with some load balancing, then we just run gradient descent on this batch with like so SDG, right? So it's a pretty simple idea, but one important detail is like so we need to do some load balancing. As you can imagine, like so the real world data is a lot smaller than the sim data, right? So if you just do uniform sampling, so the real data will only appears like so very occasionally, right? So in the kind of training set, so you want to balance out to make sure that like so the real data is very important to make sure we don't detach from reality, right? So it needs to see good amount of real data for the policy to be useful. And then we co-train on this data set running the standard SDG loop before we can get a policy for deployment. So the this figure kind of shows like so how useful are the 2 different data sources, like on par data to data cousin. You see like both are useful, but if you combine together, and they give you a small bump like in the final performance compared to only train on the real world data. Well, this seems conceptually easy, right? So we are just doing some of like a simple combination in a batch settings, and then so it's kind of like too good to be true that like, so this kind of simulation can work. But I would say that really devils are in the details, like how to get co-training to work. There's a lot of know-hows, and you need to make sure like so there's a decent amount of same data and real world data, tuning the alpha to make sure that so the real data have a good amount of presence is important. You need to align the camera a bit, not exactly alignment. We don't need like super precise camera calibration, but some alignments are needed for the knowledge to transfer. And then last, like so, the question is like so we have shown this co-training to work in simple single task settings. Whether this will work in foundation model, I will get back to this point later. Okay, so I would say that the effectiveness of co-training has been a surprise to us, like so when we first discovered this, but this has somehow been replicated like this over and over in different settings. People have been exploring co-training between sim and real data, like what we have done, but also in other type of co-training, like combining human manipulation data and robot teleoperation data, as well as like so combining like so observational data that does not have action with like a state action pair data, right? So there's different way of doing co-training explored by recent robotic literature. But of course, the very idea of co-training traces back to even earlier pioneer work on domain adaptation and self-supervised semi-supervised learning. So that kind of we see the repeated success of co-training that makes us wonder why, right? So why co-training works. We start to kind of investigate what's the underlying representation emerge from semi-real co-training. So we peek into the features of the train policy to see what's the representation of the data samples between sim and the real. So here I show you 2 features that the blue is the representation of the real data points, and the red is like from the sim. And this is like from the visual features and from the vision encoders of our policy. Is there any interesting patterns you find? I mean, they don't perfectly align, but somehow when we like do dimension reduction to project that in a 3-dimensional space, you see that somehow they share similar shape. Right, so, and this is not cherry picking. That we actually examine across a variety of tasks that we see that so this pattern is quite consistent. So, and also we kind of try to quantify this as well. We come with this like GW distance, which measures like the intrinsic geometry of different kind of feature sets, and that kind of that GW distance also confirm the fact that the co-train policy allows the same and the feature to align better. That preserve the same geometry in the vision space, right? So, but of course, like so, in the day, the model needs to output actions, and we start to see how the feature evolve throughout the network. And this is like a feature set that's getting closer to action generation, which comes from the transformer layers. Now that you see a different pattern, which the features start to align more and more, right? So now not only they preserve similar geometric shapes, they actually start to overlap in the same space. And then we have the other kind of metric called a fused GW distance that try to measure the feature alignment that also confirm that the co-train feature actually aligns better than the non-co-train feature. And then the third observation is we found is like even that the feature size looks aligned, overlap pretty well, right? So in that kind of down project 3-dimensional space. What if you train on linear classifier on the representations? Just to tell apart, is this same or is this real? the simple battery classifier task with a one linear classifier, and we see this classifier can almost 100% perfectly tell apart which is same feature, which is real feature. That means that even though they align in the low dimensional space, they still preserve some information of the domain where they come from. And this is kind of an interesting observation. I don't have an answer, so why this happens, but the hypothesis that we have now is, I think that the feature alignments help transfer the knowledge. You need to have some overlapping in the representational space so that we can harness the knowledge from simulation domain. But meanwhile, it's actually better for the model to not confuse the simulation with the real world, right? Because at the end of the day, there's some idiosyncrasy between simulation and the real world. You don't want to get confused, or you should act like a real world when it's in the real world. You should act like simulation within simulation. So it still remains an open question, I would say. So whether this hypothesis is true for co-training to work, and this is something that we're working on nowadays. Okay, so this is how we use simulation for co-training, and I want to also discuss quickly another strategy for synthetic data generation, which is leveraging this emerging cool new model of a video generation model. I don't know if you guys been following. It's kind of half jokingly that research community have been using Will Smith eating spaghetti as a golden test to assess the model capability within 2 years, and there has been incredible progress. And this is the state of our model for March 2023. So you see that sometimes Will Smith eats spaghetti with hand, right? So, and there are some kind of a similar appearance, but so the identity was not preserved super well. And this is a model from May 2025. You see, this is a multi-model generation model. You can even generate the song. Yeah, I don't think spaghetti, there's still some issues. I don't think spaghetti is that crunchy. But you see, but you see, so definitely we see the progress within 2 years. And this is also not the best model. There's new model released, View 3.1, the Sora 2, that is it's even better performance than that. That kind of inspire us to see whether we can actually leverage the progress and piggyback on the success of this video generation model for synthetic data generation. So we start to look at this models to generate realistic video from an image and language instruction. And so these are the kind of what we call the dreams data, that take an initial image as input and a language prompt, and just let the video generation model roll and to generate a video frames based on the language description. But they are not perfect. Sometimes they generate a physically inconsistent video. Sometimes they don't follow the language well. I will use another VLM just to kick out those bad ones, right? So that does not match with the language description. So in contrast with text mimic gen data I just talked to you earlier, this data is a bit different because they don't come from physical engine. They don't have action annotations. That means that we need to train another action models and to fill in the blanks, right? So we actually train an inverse dynamics model or latent action models to annotate the missing image between adjacent frames so that we can turn that into a state action pair data set to shovel into our foundation model training. So, and the concrete pipeline follows 4 steps. We take this frontier video generation model, but a lot of this model, they are not trained on robotic in-domain data. They never see how a robot arm moves, right? So we need to fine-tune them to learn about the robot dynamics and kinematics. And then we roll out this word model to generate a bunch of videos. And after that, we annotate the missing actions and to turn that into a data set and train a policy on such synthesized data source. So that's the high-level idea, right? So and in the paper that we presented, this is the core paper called DreamGen, that we just presented a few weeks ago. I will show 3 use cases of such synthetic data source. First, you can do training data generation, but also you can do behavior generalization and scene generalization. I'm going to focus on the first one given the interest of time. So the idea of training data generation is you can start with 10 teleop trajectories. This should remind you of text mimic gen, right? So we start with a handful of human teleoperation. We record that, but this is in the real world, not in simulation. And then we run DreamGen to generate tens and thousands of neural trajectories, and this is just let compute do the work, right? So we can running on the NVIDIA cluster, we can generate thousands of hours of training with 1 hour of compute, right? So we can get a lot of data from these models. And once you have now we have 2 data sets. One is 10 human demonstration, one is 10,000 neural trajectories. What do you do with it? Co-training, right? So we just said co-training. You just combine them together, apply our co-training recipe to train the policy. These are the kind of tasks so we do with this paradigm, and particularly when we design the path, we intentionally design some of the tasks. It's very difficult to simulate with traditional physical simulation. We use a Majoko for the DEX mimigen, and you see that by using some different models to wipe the dirt, or hammering with all the contact reach task, or stacking multiple bows together that have a lot of dense context. Well, if you imagine implementing this in a physical engine, you probably need to use a very expensive solver, or you need to use a finite animal modeling to model some of the complex physical phenomena. This is super easy. Constant runtime, you can just let a neuron do the inference to generate those kind of very complex things. And also, the quantitatively we confirm that adding group dreams also helps improve the robustness of the policies. I'm gonna skip the second and third, and but the idea is so you can also prompt the video generation model to create the demonstrate for the new verb, and also generalize, of course, completely new things that's beyond the robotic workspace. One example I particularly like is watering the flower, right? So you can water flower, and you see how the flower is trembling while the water heat the flower. Imagine implementing this in physics engine. It was impossible. So yeah, so these are the things I think so this type of model really shines, right? So now we have this 3 data sources as I tell you about, right? So one is robot teleop data that come from robot hardware. They are real world sensor, real world motor, real world observations, super good. But the challenge is so they're costly to collect, right? So they're quite time consuming and kind of resource consuming. And then the DEX mimicking data, they come from kind of a classical physical engine. So then the issue with that is sometimes you have the rendering gap, or so the content creation is still a challenge. But the nice thing about it is so the physical engine was implemented with some physical first principles, right? So and you do have high quality actions coming out of it. And the third 4 data sources are DreamGen. They are coming from video generation model. Well, if you look at the videos of DreamGen, they are super realistic. You almost cannot tell apart what is synthetic, what is real, right? So, but the downside of this data source is so the action can be noisy because they are predicted from another AI model. Okay, so now we have these 3 data sources, so the way that we do just co-train them together. Of course, there's a lot of nuance on how to do data balancing, data curations. I'm not get to the details of how to train this with the foundation model, but this is the kind of recipe that we use to train our latest version of our root model called Root N1.5. And quantitatively, we also confirmed so this does help with the model performance as we combine more simulation data into the training mix. So for a lot of videos that I show you today, we focus on just the tabletop manipulation, Inferno, and treating the humanoid as a mobile as a manual manipulator. As the next step, we really want to leverage the lags, right? So for it to make sense as a bipedal platform, we want to unlock an entire kinematic range of the robot to do large space or local manipulation tasks. So I think I show you this video at the core when I was presenting there. Just in case you missed it, I want to play this video again just to show you what's coming next. So this is a NVIDIA office in the background. Right? So we are running a whole body controller that trained to track human motion capture database and to generate a realistic motion completely sim. And the robot is picking some natural language commands to understand the path. And then it's localizing itself, running some kind of vision-based localization stack and in the building environments. This is running completely on board pattern, right? So there's no cables, and so it's using the egocentric camera to navigate to the target. So as the model is running, it's also running reasoning models in the background. As we remember, the task is to get the healthiest food, right? I believe. So it sees 3 objects and one potato chip, 1 cookie, 1 apple. what its health is. I think the apple. So it learned to pick up the apple, and then you adapt to prompt like the good models and to perform the actions. After it takes up, it try to navigate to the target. Then the navigation model is trained completely on synthetic data generated from a physics engine. There's no kind of real world training data. I'm thinking first that this is like 1x speed, no speed up, and also no cutting, right? So it's just taken by one shot just to keep everything real. The tasking is actually quite difficult, like so, because like this is running a billion parameter models, and you do need to get that to inference speed so that you can release the hand at the right moment to toss the operator to generate enough momentum. So part of it is like science, like how to build the models and train the models, and part of it is actually engineering, right? So to squash down the last bit of latency so that you have such kind of a onboard deployment. So that's just the life of robotics, right? So yeah, it's a combination of engineering and science. So Guanyan, how much time we have?
I think it's okay. We have the room till 4 p.m. I think you have 5 or 10 more minutes.
Okay, so I think so. I'm just gonna conclude here today's talk, but I want to throw some final thoughts out there just to conclude. I think, as I said, that humanoid local manipulation that leverage a whole body control is a real big deal, right? So we see tons of videos of humanoids doing dancing, jumping, kung fu. That nice showcase of the robot hardware capability, but like so, local manipulation is the real value creation task. It is the killer architecture of this kind of bipedal emerging new platforms. I make this tweet. You can feel free to follow me on Twitter. So I make this tweet saying people who are really serious about robot learning should make their own robot hardware. This is, of course, an extension of Alan Kay's original quote, if you know. People who are very serious about software end up making their hardware, right? So this is just my personal reflections and inspired by Alan Kay's talk. Is just all the kind of pain and suffering working with current humanoid robots. Is that I think one side effect of working on humanoid is you really start to appreciate your own body. Right, so I'm gonna start to look at my body all the time. Why I have wrist and why I have necks. So I think like what evolution does to us is, for the millions of years, is truly amazing. That a lot of like biological design, just like if you look in retrospect, it makes so much sense why we have toes, why we have spine, why we have such a flexible neck for active perception. All right, so this makes so much sense for it to build autonomy. I think so. Currently, the humanoid hardware, there's still iterations of designs, like so to refine, to improve. The current hardware makes the AI problem artificially harder, right? So if we have dexterous hand with good like a tactile sensing, that can significantly reduce the computational challenge of building robot autonomy. But I think I'm still very bullish and optimistic about where things are going. I think so. We have made a lot of progress, and we're still in the early stage of humanoid commercialization. If you ever think about building a business, but we see progress are accelerating. Like so, we see the progress of how people climb up the liberal benchmark. We see the amazing progress of video generation model. These pieces are coming together, right? And we now see humanoids start to deploy in some settings like factories and warehouses. You can order humanoids and to ship it to you in the next few days at the price of a car. There's an open source humanoid design, open source models like good for you to use. Apparently now you can pre-order 20,000 robots shipped to your home, right? So who knows? Like so, I think there's a lot of opportunity, also a lot of excitement going on, but also there's a strong societal needs for robots and automation, and some of the long-term challenges faced by humanity needs this type of a solution, and also there's a big business opportunity that associates this as well. So in my opinion, humanoid is not a question of if, but it's a question of when. Okay, so but this is definitely beyond any individual or any single institution can pull off alone. Right, so that I hope that through all the opportunities and challenges and to you, so that can kind of maybe inspire you, or more of you can share the same vision, so that we can work together towards the North Star goal of building generalist humanoid robot. All right, thank you.
All right, we have like 10 minutes for questions. If you want to leave earlier, please do it quietly. Thank you. Any questions? Where we go? Sorry, I cannot tell who is the first one who's hand. Yeah, Aru, go ahead. Yes.
Hi, Yuke Zhu about the shop. So my question is about code training or the necessity of code training pipeline. So did you get a chance to compare the work performance from using pre-training, fine-tuning baseline versus code training pipeline, given that you have exactly the same amount and diversity of data set, for example, the same real robot data, same data from digital cousin, digital system bro, digital twins, and the same, exactly same prior data. So comparing these two pipelines, which one's better and what are pros and cons?
Great question. So I think so when you are saying like so fine tuning, you mean first train on large scale simulation data and then you fine tune only on the real data, right? Yeah. That is actually a baseline that we test before we run the code training. But somehow we found out like so you do need to see the heterogeneous data sets the same time to get the best performance. This is still interesting why this happens. Like I imagine like so seeing some real data while you are training on simulation allows the model to figure out what's the kind of like the representation, what kind of knowledge you want to extract from the simulation. So that's why I think co-training by combining the data simultaneously works better than the stage training, first pre-training in sim and then real. That is a viable approach to leverage different data sources, and we have that as a baseline.
Yeah, thanks.
So, hi, thank you for the talk. I've used ChatGPT before and had it generate incorrect or manipulative responses. I'm curious, how concerned are you about the potential danger posed by a robot foundation model acting in a physical way that's erroneous or erratic?
Yeah. I think safety is like a very big issue for sure. And actually safety is not stopped only at the layer or cognition layer, right? So it's actually the full stack from the high level AI all the way to like so the functional safety under even the hardware side. So particularly for the VLM and the VLAs, like so definitely these models can go wrong and they can offer like so imperfect or sometimes erroneous actions. So definitely you cannot take those actions at all the time, right? So there must be some type of a safety check and guardrails to make sure that like so it does not like so accidentally generate like so malicious behaviors. So I don't think like so the autonomy of the robotics will be as a model, but I see that as a system, right? So the foundation model is a component of that, but like so the actual action generation should go through a pipeline where the safety check and the guardrail should be a critical component of that.
I know you said earlier, like generated data could have like some noise and that could be somewhat detrimental at times. Wouldn't noise sometimes be beneficial for training?
Noise sometimes serves as a way to do data augmentation, but particularly the kind of noise I see is some physical implausibility with those like video generation models, and it's actually not too hard to prompt those video generation models to generate a kind of magical videos, and that's not kind of real, right? So particularly I think because those data are trained mainly on visual data, they don't really have like all the contact information. So penetration and all this kind of close contact modeling remains to be some kind of unsolved problem. So penetration actually occurs the model training and
Sorry.
So what do you the biggest sync-to gap right now? Is it like friction, or is it contact penetration with magic, or is it like dynamics? Is that an electrical system or any integers besides
Yeah, there's like so many factors of like a semi-real collaborating. There's a visual part, there's a physics part, there's a robot dynamics part, right? So there's like some semi-real gap, like so all over the place. But particularly, I think like so the most critical is to get the physics right. I think for visual, like so we now have a quite robust visual representation from all those like so pre-trained vision backbones, and they can actually bridge the semi-real gap by and large. And also you can go through some like a domain randomization, data augmentation to increase the robustness of the visual pipeline. But for the physics parameters, like so what you mentioned, like so friction, mass, and articulation properties, like so it's so important to get those right. And when we want to apply this technique to physical contacts and contact-rich tasks.
Funny. So like robotic evaluation is like huge problem that we face today. And there's different approaches like evaluating model policies in role models or simulation or in the real world. And I was wondering if you had any insights or ideas about what is the right way to go about evaluating our policies and making the right decisions.
So evaluation is to me so it's actually a harder problem than developing new models. Yeah. So I think so one thing about working in these models in industry setting is that there is GPU reach, right? So we can like so explore so a lot of like ideas in parallel. So but ultimately like so how fast we can make progress really kind of determines like how strong is the signal, like tells like the good idea from the bad ideas, right? So that boils down to having a systematic evaluation protocol that allows us to give us the most informative signal, what works, what doesn't work. So as you mentioned, like so there's a different type of evaluation. You can do evaluation in the physical simulations, like what we also do as well. So a lot of like so early model prototyping are done with simulation. We also have a Libero, we have Rubacata, we have a lot of Isaac Lab simulation environments that we use day by day. So I support this kind of evaluation. So far, I think there are some promising signs. Like so, if you evaluate in SIM, they show some good correlation how the model performance will be like in real, but not gonna be exact match. It's not like so you get 50% in SIM, you will get 50% in real, right? So I think that's still an unsolved problem. Meanwhile, I think the video generation model are also making progress and towards adding controllability and interactability. That means that you can actually turn that into a real world simulator. You can actually kind of make them action conditional. You can put different actions to use them as a newer simulator. I think this is where the field is going, and we are also investigating this line of work. So potentially this can be another type of simulator we use to evaluate our model that has a bit more realism in terms of like the task coverage and also the visual appearance. But right now, ultimately, real-world evaluation is a golden ruler. I don't think you can skip that, right? So like you can do simulation and a word model to do early kind of model prototyping, but ultimately, real robot evaluation is something that give you the most informative signal of what work doesn't. Yeah. So that means like so part of it is like the hard part is like so how to do systematic real world eval, and you want to make sure that you don't have any bias, introduce any bias into the object placement. You want to do A/B testing across the models, and there's like a lot of like nuts and bolts, right? How to do the real world evaluation right. But also there's like some kind of CI/CD pipeline, so allows you to do quick turnaround time from model training to model evaluation, and then back to the model training.
Nice. Sorry, I don't know where's the ultimate order. Anaya? Yeah.
Can you give me an example of a manipulation task that your models are still consistently failing on? Because I want to understand what the bound is for research engine.
What's the kind of manipulation task that consistently fail? So I don't think it's too hard to find a task. A model. Yeah, I think the opposite of the question is like, what would be a task like the model constantly works? So that's the point. Yeah, but part is like actually, I think like I personally I'm very excited about dexterity right? So I think a lot of the useful tasks we see in everyday homes and also in factory settings that involve tool use or dexterous hand for contact reach assembly. So those are a lot of the tasks that we are focusing on for now are pick and place tasks. But I don't think we are the one to blame, because the hardware I think is right now mostly support this kind of simple force manipulation, pick and place type of behavior. Hands are definitely gets better. Dexterous hand tactile sensing, that was likely enable us to kind of explore more on the more dexterous and a contact reach manipulation. But these are the family of tasks I think is have a lot of very important practical value. To get there, we need to have good co-designs of both the hardware and also the software.
Well, hi. It seems that current humanoid robot policies seem to split locomotion and methylation two separate parts and then combine the inference time. I'm curious if you see a need for simultaneous locomotion and manipulation in humanoids in the future, and if so, how would we achieve that?
Yes, indeed. So, and I think also in the video that I show you, and some part of this controller is actually done by a whole body controller that we treat like upper and lower body movement as whole. That's how you can run and jogging while coordinating with your leg and arms together, right? So we're moving there, but you're right. So a lot of the cases, so decoupling them makes it easier. That you just train a lower body balancing policy or walking policy, and upper body you can just treat as a manual manipulator. In some tasks that requires local manipulation, that assumption fails, right? So if you want to bend down to reach an object from the ground, or if you pull spring-loaded doors, you do need to actuate the whole body to perform those tasks, right? So that what requires us to build an integrated solution that build a robust whole body controller that can generate those kind of versatile and the natural movement, and also figure the right interface to let the whole body controller interact with the VLA models.
Yes, has 3 more questions, but go ahead. I had a question about the data pyramid. Like right now, all the layers are mostly passive demonstration data. How sufficient do you think that is, and is it necessary for more deployment, like continual learning? I guess this is the question.
Continual learning, great. Yeah. So I think so right now, what we are doing is kind of, if you think how LLM and GPT are trained, there's a 3 stage, right? So you do pre-training, you do SFT, and you do RL, HF. Right? So we're in the first 2 phases of training, right? So you can draw analogy that so most of the time are pre-training. Pre-training is actually most important. That's where the knowledge accumulation happen, right? And then you do something like a SFT or post-training to adapt to the downstream task. But I don't think the policy will be perfect from this kind of supervised post-training paradigm. Maybe it will have a high success rate if your pre-training model is good, but there's some fundamental limit of imitation learning, right? Because imitation learning is distribution matching, right? So you want to match the state action distribution in your training set. It does not necessarily understand what's the goal of the task, right? So reinforcement learning is about maximizing the long-term reward so that you do know what's the objective of the task is, right? So, and that's important to close the final performance gap, in my opinion. So I don't think the complete training will be done, right? So after these 2 stages, likely after we deploy the robot will not be perfect. And then learning are still gonna happen on the job, right? So you're gonna collect more data and keep refine the model performance as new experience accumulate over the runtime during the deployment environments. And that's some kind of a RL loop that we call data flywheel, right? So yeah, and we are doing some research, and I present this liberal paper that so we are start to do some real world RL, but this is just I would say a beginning.
Wait.
I have 2 questions. First question is, do you think 3D reconstruction will have something to do in this field? That probably for generating the synthetic data or something.
Yeah, I think you already answered your question, right? So generating the static environments are closing the loop. The real power of sim to real hinges on we make real to sim happen, right? So we need to find a way to generate realistic simulation, bring more real world into simulation so that the sim to real can really shine. And that's where I think lot of the roadblocks and for making real to sim to shine is some kind of fundamental computer vision problem. Like so getting like so 3D reconstruction SLAM to work for in the wild video and the image data sources.
My second question is like, do you think VRA is definitely like a certain approach we'll adopt in the future, or we can also do something like VRM agent, just use like something like 3D object detection, and then we generate 3D pose onto the objects. Then we plan the whole pipeline like long-term task or something like this.
I think the jury is still out. Yeah. So like there are a lot of domains like so it makes sense to use some skills as APIs that you can call. You just do a VRM planning. Say you do like say machine tending that you can perfectly describe the robot behavior with a bunch of primitive. It's just a matter of like setting the right argument for those skills to be called at the right moment. For those cases, it makes sense to use a VRM plus some hybrid approach, right? So, but for general purpose autonomy, you cannot kind of limit to or find a set of skills or behavior, right? So for that, so we are a type model, provide that kind of flexibility to model arbitrary behavior. But I wouldn't say that so we have the final architecture for BLA, right? So I think there's definitely architecture research needs to be done.
Right. I think everyone likes it, so let's have 5 more minutes. If you don't mind, you could.
Your mind.
Yeah, and nobody asking specific question. Let me ask a specific question first. I'm trying to push back a little bit. It's like I think that there's a lot of people in the community, not me, believe like real world data is the only way to go. We need to first train pretty exceptional well real world data. Otherwise, you're gonna learn something like a Spork, right? Like Sergey wrote a blog like Spork of ATI. I'm just curious, what do you think about this? Especially like like company like 1X, they already deliver the real humanoid neo to a home, right? And they're gonna do a lot of operations, and data file will start. It seems like you no longer need simulation data or like video data. I'm just curious, what do you think about this?
Good question. Yeah, I don't think this is spicy enough, right? So so I think people, I mean, real data is king, right? So if we have a way to pack a large volume of real data, why not, right? So that's the best data. Or just like but the question is like, how do we get there? Maybe this is not a technical question, right? So whether we should use real data or not. I also agree with like so all the other companies are doing real data capture as what we are doing as well. So you need the real data so that we don't detach from reality. You need to see real sensor, real hardware, how real motor moves. But the question is that it's more like an economic question about how do we get to the real world data. Is it kind of a $1 million, $1 billion of a teleoperation enough or not? I think nobody have the answer. Part of it is like we don't really have a good understanding of the scaling law of like this kind of VLA model. So I think the way that I see is like the training will happen in 2 stages. So first, like so to be able to deploy robots in the wild and to collect that large amount of real data, the model needs to have some base capability first. Meaning that like so the robot is able to perform some basic tasks so that it makes sense to reach certain level of a widespread deployment. Then once you reach that level of a deployment, and then you can start the real world data flywheels, right? So, but I think the data pyramid, to me, is a viable approach to solve the bootstrapping problem, right? So before we deploy millions of robots in the wild to collect data in a Tesla way, that we got to find some way to bake in some basic capability, basic functionality, so when they turn on the robot, it does something useful. So it makes economic sense for people to buy robots, put robots in the real world problems, and then to turn the data flywheel. Eventually, I actually hope like the data pyramid will be flipped, right? So the real world data should be the largest amount of data, but that hinges on how do we solve the chicken and egg problem to bootstrap the level of autonomy to be the level of good enough to reach widespread adoption and deployment of robotic systems.
Makes sense. Okay. Yeah, Nico. Sorry, you raised hand first. Yeah.
Hi, bro. So I want to kind of follow up on the robot evaluation pipeline. So you mentioned that real world evaluation is important, and it is definitely important, but major bottleneck is you have to do research and then you cannot make it's very difficult to make statistically significant comparison there. So do you think the co-training principle can be used there as well, right? You use some real world predictors and simplicity and train a world model and then evaluate on that. So kind of philosophy can work, in evaluation.
Got it. So you mean like so using co-training to improve the word model so that you can do evaluation in the word model? I think that's a good idea. There's actually some like research papers and recent publications showing that so if you mix in some synthetic data coming from physics engines in the word model, it actually helps improving the physical grounding of those video generation model. You can generate more better physically plausible videos because those data points are coming from physics engine, right? So they have like a good amount of physical knowledge embedded in those. Right? I imagine so that can be a way to improve the word model, but I will say that like so compared to VLA training, where we need action data, a word model, they have an easier job to scale. Yeah, because like so to train those video generation model, all you need is just like a abundant video data, right? So we don't necessarily need action data. So there's a sufficient amount of like a real data for the video generation model community to make progress as for now, right? So I think synthetic data can play a secondary role there, but it's not as critical as like a VLA training from what we are seeing.
Yeah, thoughts. Oh, do you think it actually like the robotics or leave land anymore? Because I was working on land, but when I think about it, like all the output like VLH friend and be a reflection on my job and biological humanoid, I don't actually need to remember my like code at a millimeter scale to do all complicated tasks. So do you think eventually will leave land in the big data?
Future of robotics. Wow, this is a big topic. Yeah, I mean, slams are like running everywhere. I think the robotic system in autonomous driving cars, in your Roomba, vacuum cleaners, there's definitely roles to play. And maybe you are seeing like so, particularly in the context of a general purpose robot, can the VLA just handle everything that we don't need a slam at them day?
Two more questions. Yeah, Tom. Yeah, I have a question. So about like representation of good idea. How much do you think like a generalizability come from the availability of better and more powerful like VL? Like how much does like the VLM's representation space like infers like transfer the like for example the motion composability or like the motion generation?
I see. Yeah. Well, there's a generalization across different aspects. There's like a semantic generalization that you see that works from Google, where they show that a push object to Taylor Swift that requires you to understand which one is Taylor Swift in the picture, right? So that level of generalization, definitely VLM really doesn't match it, right? So because like it's trained to encode that kind of semantic knowledge, the concept of the word. But there's also other type of generalization that's more goes towards the system one on the behavior level, right? So how do you actually sensitize trajectories and compose them to solve like interesting tasks? That part we have seen only the VLM is not sufficient, right? So you do need to kind of find ways to systematically generalize in the behavior side. I think that's like still the really hard part is like how do you figure out a way to achieve systematic generalization in behavior, not just in semantics. This right now a lot of the generalization I would say come from like so dataset augmentation, the way that like we do text mimicking, right? So that's the way to achieve some behavior generalization because you do start to see more diverse behavior grasping object from different angles from different locations, right? So like by augmenting the data sets, we achieve better behavior generalization. But the question, I guess, is like, so whether we can upstream those generalization to the VR backbone so that we can build that kind of like a better VR backbone that encodes those kind of behavior generalization capabilities so that we can reuse this like across tasks and domains.
Sorry, last questions. Sorry. Kashu, maybe? Sorry, we can be out 2 minutes after the talk, so yeah.
Following up the data collection thing, so I think the action is tightly connected to the embodiment of the robot. And if you say like you collected like real world data, do you think you can like use for the other robot, or like what's your thoughts on the cross embodiment thing?
So, well, I think like the model that we train are cross embodiment, right? So we are able to kind of do the kind of action representation of live through by kind of branching out from the action output hat then to be able to train one model that for all embodiment, right? So but whether cross embodiment actually helps transfer knowledge across across different embodiment, whether it gets good amount of synergy or positive transfer, I think that still remains to be seen. And I think another question is like whether this kind of BLA is the right architecture to consume cross-embodiment data, or we should combine some word modeling capability that the word models and like the video generation model are naturally embodiment agnostic, right? So it's just one model you can apply to human videos, you can apply to different robots. Maybe one way to go is like combine this kind of word modeling capability into the VLM so that we can form some kind of omni model that can perform both, so that we can also leverage better cross-embodiment data, right? So that's like a very active ongoing research topic we are hinted on. But I think like I would love to see cross-embodiment working, because like it's not just for the sake of supporting the robotic ecosystem, but also I think like so it makes economic sense that we can reuse the data we collected in the current humanoid. By no means they are going to be the final form factor, right? So if we spend millions collecting data on this platform, I would love to be able to reuse this and extract meaningful knowledge and from the data set we collected on this embodiment.
Okay, the final career-wise question for students. So it seems like a lot of research you show here require a lot of resource, like computational resource and GPUs and robot. So what do you think, like PhD student, especially PhD student, should spend 5 years? What research topic do you think they should work on in the era of, it's yeah, BLA and all this, yeah.
Yeah, well, great question. Yeah, I can tell you which work that I presented on my university work, which one are like the NVIDIA work, right? So I think there was a clear divide. Like, so we first figure out like how to do the autonomy object-aware retargeting, and then we extend to text imaging. All the foundational work are done still at the university setting. You don't really need a lot of compute to train small policies and to get the idea off the ground. But the big large-scale pre-training across thousands of machines, that's like my NVIDIA work, but they're naturally divided. I also present a little bit about the science of co-training. That's just my intellectual curiosity, and to me, those kind of more foundational understanding, deep science should be done in university setting with this kind of intellectual freedom we have. And I think so we're not just doing this for fun, right? So and that kind of a deep understanding will eventually close the loop to inform the next generation of our foundation model building when we scale up as well. So that's more like the natural divide, and also plus that I see that this challenge is so big that I don't think anyone can solve that. Closed door, and so there's a lot of open source and the open models available, right? So as a student, I think also leveraging those kind of existing open source tools, and that's another way to kind of still do some fundamental but also cutting edge research.
Thank you so much. Let's